Hi, I'm Han-Seok from Iris Lab at KAIST. In this talk, I will introduce twisted string actuator-based exoskeleton for hip assistance in lifting tasks that is aimed at preventing low back pain and injuries in the vocational setting. A large number of workers suffer from low back pain or related injuries during heavy lifting tasks in industrial and manufacturing settings. The main source of these injuries and pains comes from lifting heavy loads. During the lifting motion, high tension is applied to the lower back muscle and the disc is compressed, which leads to the low back pain. In order to prevent potential musculoskeletal disorders during this weightlifting motion, various types of hip and back support exoskeletons have been developed. Most of them connect the electric motors directly to the hip joint through a conventional gear mechanism like a harmonic drive. However, high gear reduction often comes at the cost of low back durability and decreased user safety. As an alternative to geared motor, pneumatic actuators have been also extensively used. However, when high pressure is supplied through a cable from an external pump, it may cause inconvenience to workers during tests. Therefore, proper selection of an actuator and the transmission system plays an essential role in the exoskeleton design. Now, let's consider the twisted string actuator, or TSA, which we have used to develop our exoskeleton. TSA has been used continuously in the development of several types of exoskeleton due to its many advantages. TSA has been established as an effective actuator due to its high gear ratio and efficiency, and low weight, inertia, and cost. When the string is being twisted by the relatively low torque, it produces the high linear force while contracting. Thus, when the string is twisted, it acts as a gear with a nonlinear gear ratio. We have designed our device to take advantage of the variable nature of transmission ratio of TSA. To design the exoskeleton properly, we firstly need to find the requirement for lifting the target failure. For this, a simplified bi-kinematic model was used to calculate the additional torque required for the hip joint when lifting a 10 kg load. To obtain joint angle data, we have performed the experiments and recorded the joint angle values during lifting the object. So, we calculate the required hip joint torque and angular velocity during lifting a 10 kg load from stoop stand position. At the beginning of the stoop stand motion, comparatively large torque is required, then its value gradually decreases during the motion. This torque profile closely matches the shape of TSA's transmission ratio during twisting. Therefore, TSA can fit the application well if it is designed properly. We have developed the TSA-based exoskeleton to take advantage of variable gear ratio of TSA. Our device can help to prevent low back pain by supporting hip joint rotation. This can compensate for the added hip joint torque due to the load on the hands. For designing our exoskeleton, we choose the most straightforward way to make the device as compact and lightweight as possible. The string of TSA is routed along the wearer's back to the hip joint. The motor torque is converted into a large linear force through a twisted string. Then the rotating pulley with this force generates a large torque at the hip joint. So one of the key design parameters of the proposed exoskeleton is the pulley radius RP. It determines TSA length and stroke and also affects the torque generated at the hip joint. The minimum pulley radius is calculated with the maximum hip joint torque and the maximum tensile strength of strings to prevent string breakage. The maximum pulley radius is calculated with the maximum rotation angle of the pulley and the contraction ratio of the string to prevent excessive twisting. This means that the pulley radius RP can be anywhere between 12 to 111 mm. To calculate the achievable torque and angular velocity of the TSA-based exoskeleton, the gear ratio between rotor and the pulley rotation was taken into account. Assuming that the generated force on the twisted string Fs is converted into pulley torque tau P with non-ideal transmission efficiency, the gear ratio can be obtained simply by multiplying the transmission ratio of TSA with the pulley radius Rp. So, the overall gear ratio is calculated with the length and radius of string, the maximum hip joint rotation angle, and the radius of the pulley. Once all parameters have been determined, the gear ratio is simply a function of the pulley rotation angle. In order to satisfy the requirement in all hip joint angle range, the gear ratio range was set as follows. The minimum boundary is determined by a motor and pulley torque, and the maximum boundary is determined by motor and pulley's angular velocity. Once some of the parameters have already been determined, the gear ratio can be designed by adjusting the pulley radius, motor torque, and angular velocity. Constraint area of gear ratio can be designed with the selected motor torque and angular velocity. If the pulley radius is adjusted and placed in this area, the requirement can be satisfied. In particular, as the minimum and maximum boundaries are close to each other, the exoskeleton can be designed with the minimum motor power. Through the design gear ratio, it is possible to estimate whether the targeted hip joint torque and the angular velocity are achievable. In particular, it is possible to estimate the minimum motor torque and angular velocity to satisfy the requirements. The developed exoskeleton has a pair of TSAs that is located beside the hip joint starting from the back of the shoulder. It contains a harness and mount for supporting the upper body, hip, and teeth. The strings have been guided inside the hollow cowl 5s and connected from the motor shaft coupling to the hip joint pulley. The total weight of the system, including the battery, was measured to be around 6 kg. The wearer manually controls lifting and lowering the sequence by wearing gloves. The maximum motor torque and angular velocity are limited by the design parameters. During the experiment, the wearer performed a stoop stand motion while holding a 10 kg load in their hands. This graph shows the measured hip joint torque and angular velocity of each hip joint by evaluating whether it achieved the requirement. At the beginning of the experiment, the low torque is shown in the initial stoop hip joint angle, but as the experiment progressed, the required torque was achieved by adjusting the hardware compliance. By limiting the motor torque and angular speed, the problem of exceeding requirement was adjusted. Finally, the hip joint torque that can be assisted with the TSA-based exoskeleton is approximately 20 to 90 Nm. In the case of angular velocity, up to 110 degrees per second can be supported. In the future, the use of low-power motors will be considered for a reduced power consumption and weight. If you are interested in our research, please contact us for a mutual knowledge exchange. Thank you.